Good morning. Let us resume our discussion. So what were we discussing in the last class?
We were talking about image segmentation and how there are three types of segmentation: semantic, instance, and panoptic. And then we went to approaches to segmentation, starting with the histogram approach, where we studied about thresholding. And then we moved to clustering based approach using k-means clustering. And then we saw some slides based on examples of this segmentation.
Okay, good. So in this class, let us discuss on the depth estimation, especially on the 3D reconstruction. 3D reconstruction in general can be done in several ways. 3D reconstruction from images. So we will see some of the overview of 3D reconstruction methods. And then we will discuss further on the stereo-based 3D reconstruction method. So as we discussed before, so in computer vision, few of the problems are the some of the major problems of interest lies in 3D reconstruction as well. So we have seen that first recognition, that is actually recognizing the objects, identifying where they are, which they are, what are those objects, and so on. And then reorganization. Reorganization essentially mean it is segmentation. We are trying to see to which class a particular each pixel in the image, to which class it belongs. Okay, that's the reorganization essentially. Essentially, the segmentation are identifying with each of the pixels a associated class labels. Okay, and then the third important aspect of computer vision is reconstruction. Reconstruction essentially mean here reconstructing the objects that are there in the image or the scene from the images itself. 3D reconstruction of the objects from the images. So you may have usually when we take an image, what information we have is the 2D projections of the scene in terms of the respective intensities or the reflectance values. That doesn't give us the perception of depth directly from the images. When we essentially make a 2D projection of a 3D scene, one dimension of it is lost. Then the question is, how do we reconstruct it? The need for this is, there are many applications which need the 3D reconstruction or the 3D information of the scene. For example, if you are driving and if you want to pick a object and place somewhere by a robot, what we need is to understand the three-dimensional structure of the scene. Say, for example, if you are driving, we would like to know how, what is the distance of the object, nearby objects, and then the closest object, are there obstacles in the path, etc. Okay, essentially, if you would like to pick and place a kind of an object, or if we want to perform any of the tasks in three-dimensional world from the images, we need the 3D reconstruction. Okay, so as long as if you would like to infer something, two-dimensional aspects may be sufficient. But if you would like to perform some task in 3 dimensions from the images, 3-dimensional information of the scene is very much essential. So 3D reconstruction plays a major role in computer vision. And in fact, it is one of the very fascinating application of computer vision, which can really demonstrate the impact of computer vision in real world and real scenarios. Driving, self-driving cars, as you know, are one of the typical example of it. So what we wish to see is when we make a 2D image of the scene, we essentially see a object into, that means we project it. So we only have the 2D information. Now the question is, how do I get the 3-dimensional information of the object? As I mentioned, there are several classes of this 2D image. Okay, and hence 2D projections are also there. We need the 3D information. How do you extract 3D information? before I discuss some of the methods, can any of you give how humans perceive the depth? So how are we able to visualize? We also have two eyes. Effectively, we assume that this scene is projected on the retina of the eyes, and then we have a 2D image of the scene at the eyes, okay, at each of the eyes. Then how are we perceiving the depth? Do you see any cues or any clues for perceiving the depth from the vision we have? So I wish to get some couple of ideas from you before I start describing some of the mathematical aspects involved in this 3D reconstruction and 3D understanding 3D from 2D images.
Distance from eyes.
Yeah, that's the question, right? So how do I get the perception of the distance from the eyes? That's the question. Ideally, we should be able to see only the images of the scene, because we assume that it is projection is made on the on the retina for the physical scene. So in general, what are the cues that help us to get the distance? In different scenarios, you can tell what are the clues that help us to get the distance. Yes, some of the cues which you have been looking at or observing in getting the 3D reconstruction. Can't you tell? Yeah, what are the clues that you think are helpful in getting the 3D information from images? When you see, what are you observing to get the 3D information?
The boundary of the object.
The boundary of the object, very good. Yeah, what else? What else are helpful for you to get the 3D information from the when we see? See, you have seen a big corridor. Okay, assume that the corridor is with tiles. Okay, and black and white tiles. Do you see that the corridor is how much distance like the corridor has, etc.? Or don't you see that it is a long corridor, short corridor? Or what is the depth perception? Is there a sense of depth that we get by looking at this kind of image or not?
Yes, sir.
Yes, sir.
Yes. How do you get it? So black and white tiles. Okay, it's a corridor, big corridor. Assume that. How does it look for you?
Inclination.
So inclination means?
Inclination.
Yeah, what does it mean? Inclination means I need a little refined word for it. So if you see the corridor, do you think that it's all looks, say it's a rectangular corridor? Okay, purely rectangular. Do you see that it is purely rectangular when you see? So ideally the corridor is like this. Okay, but when you see it, okay, you are seeing like this now. If you see it, how does it look like when you see it? Yeah, what do you mean by inclination? You have said something, right?
Convergence to one particular point.
Very good. So it appears that this closely converges. Slowly it will go like that. Okay, if you see somehow, if you visualize, okay, till the infinity, then it appears that it may converge to a particular point at infinity. Is it not? So you see that you doesn't look like this is what we perceive. Okay, this is the perceived one. And this is what is the actual. Okay, textured pattern. So when you see essentially the texture, it will be much more clear. Even on plane, you can notice, because we can easily identify even with the plane, little bit of this is because this is tied with some kind of project to transformation or 3D to 2D transformation that appears on the eyes. Okay, so a 3D object, when it is seen, the nearby things will look little bigger, farther things look little smaller. Okay, because of that, you can see this kind of, and then project to transformation also helps us to see that. And when there is a textured pattern, you can clearly see this kind of variation. Okay, so one clue for it is even texture helps us to recognize 3D information. Okay, so depth from texture people call. What are other things? If there is a light variation.
Sir, I don't know exactly, but sometimes a shadow can be
very good.
helpful.
So shadow will help us, especially where do you notice that? In pictures, for example, in videos or cinemas, what they do, they create different kind of shadow effects to see, have the perception of real perception of depth. Okay, even the face with a different kind of shadow looks more realistic than a completely plain. So shadow also helps. Depth from shadow. What else? Similarly, similar to shadow. What else?
So can the size of the object also affect?
What do you mean by size of the object?
Means based on the size of the object in the 2D image, like if the object is of smaller size, it can be of farther distance from the the transmitter of the signal.
Okay, that's what we are trying to get a sense of, right? We are assuming that the size of the object itself you want. See, if the object is very uniform, it is, say if it is like this, then you are what you're saying, if same object is near and farther, you can notice that differently. That's what you're saying?
Yes, sir. Yes, sir. So the depth can be estimated in that way.
Okay, so that's fine. So relative to these objects, you can estimate. That means you're saying that since the different objects are at different locations, you are estimating the depth. That happens different distances, we are estimating the depth. That is true. That is the key object, like the key principle of stereo. Or when we have two images, what will happen is the projection of a scene point will not be at the same location in the two images. That's what we will discuss now. Okay, how essentially having two images, two eyes or two cameras will help us to get the sense of depth information. So what essentially will happen is an object which is farther will look smaller for us, and anyway nearby object look bigger for us. That's one thing. Even the projections on the eyes also have a difference when it is nearby and farther. That we will discuss now. So essentially the other thing is depth in sense from stereo. Okay, it is in sense distance. It directly characterizes the distance. Okay, with respect to this distance. We also have depth from shading. Okay, and then depth from shadow or shading as well. And then depth from motion. Okay, when object is stationary, you may not perceive as being 3D. Okay, when it is moving, of course, we can perceive. But if a sequence of images are given, you can easily show that there is a 3D structure there. But if a single image is given, we may not be able to identify that much effectively on from the depth from it. So like the depth from stereo, the distance keep changing when the objects are in motion. That also helps us to get the depth information. Structure from motion people call. Structure, depth are all same. Depth essentially is the distance from the camera, and structure is the 3D information. These are all different ways. Now let us discuss more in detail about the stereo, depth from stereo. The reason why we discuss depth from stereo in more detail, because it is one of the widely applied technique, and this gives absolute depth and easy to perform with a little bit of calibration, easy to estimate with simple calibration. So what we have is, assume that we have left and right images. First of all, assume that, say, for example, there is an object here, whatever may be the object. Just for simplicity, let's take an object which has a corner in it. Okay, and then let's have the model of the eye. So usually what we assume is, if we have two eyes, okay, this is assume that left eye and right eye. We assume these are like pinhole cameras. What do we mean by pinhole camera is? So we assume that if we are seeing a point, whatever the point we are seeing, okay, this point now will cross this, okay, and then form the image at the focal length of the camera. So assume that there is a plane here. Okay, so usually what happens is, if we have a camera, the image gets formed in the camera at the focal length. Okay, it is known that on the back side it forms the inverted image, and at the front it forms the at focal distance from the camera lens, it forms the direct image, okay, of the scene. So we assume that for simplicity, we assume that this point has actually has a reflection here. And we, in general, it is a 3D scene. So we convert it to 2D image. So you can consider that this is a 2D image. Similarly, here you also have actually at the focal distance. Okay, so this is how it is formed. So what can happen is, based on the arrangement of these left and right cameras. So assume that the camera is here. I'm just showing it as a eye. Okay, so for time being. So assume that this is eye. Okay, left eye and right eye. Fine. And usually they, as I mentioned, like a pinhole, they consider. That means the object rays will go through that pinhole and then form their images at the corresponding at the image planes. So object is usually seen in a 3D coordinates. So usually object, if you would like to represent the coordinates of the object, we will have x, y. In fact, x, y, you can also consider x, y. Okay, and then z. So any point in the scene is x, comma, y, comma, corresponding x, y, and z coordinates it will have. Okay, for the scene point. Okay, and then on the images, what this, as I mentioned, this is IL, left image, and this is IR, right image. So here it will be in pixel space. So, and hence, since let me just try to see if I can draw this a little more properly inclined. Okay, so if you see here, this also will have coordinates in image space, in this image space. So if I start this with 0, 0, it's our convention. How do you wish to start? This also 0, 0. Then what will happen? From here, it will have some value of, say, you have actually x coordinate, xl, comma, yl. Similarly, you have here, so this is also, if you consider xr, comma, yr. As you can see here, the scene point x, comma, y, comma, z. Okay, a real object or the scene point. Okay, we'll have its projections. XL comma YL here. Okay, and then XR comma YR. And this is the process that happens. If you have single image, the single camera, only one projection will appear. Now the question is, given this information, can we get the details about how far, okay, is this object or scene point from the cameras? So essentially, if I assume that this is the axis on which, or this is the both are horizontally aligned, left and right image cameras are horizontally aligned, like like eyes. Then we would like to see how far is this scene point, okay, from these reference line, okay, from the camera reference line. Okay, so this actually there are, in fact, I am not elegantly defining all the coordinate system. Usually what they define is, for this this is camera, right? In our case, eyes are cameras. And then we will have actually camera reference, say camera coordinate system. Like you have actually XYZ real coordinate system. Okay, these are real coordinates. You have camera coordinate system and you also have image coordinate system. In fact, their math is a little bit involved, even though not too much involved. So when you have actually, usually what we do is, for the camera's coordinate system, we consider this as the origin. Okay, and then this is XY. This is the origin, and this is same direction, XY. And of course, camera, if you see in 3D, you can also have Z here. So what usually they then XC, YC, and ZC will come here. What usually is involved is, see the scene reference plane or the three-dimensional reference plane or real coordinates that I have mentioned may have a translation with respect to the camera coordinate system, may also have a rotation with respect to the camera coordinate system. So what do we mean by real coordinates? Are the scene coordinates are from which reference plane are am I measuring the coordinates of the object. Okay, those are the real coordinates. From there, the camera coordinate system may have a translation. So you may have actually XC, YC, and ZC ideally if you see. Okay, these are related by a rotation matrix. Okay, with respect to the X, Y, Zs. Okay, and also these may have a translation. We usually assume that these coordinate systems are related by rigid body transformations. Rigid body transformations meaning like only rotation and the translation, no shear. Okay, and then the body is rigid. The distance of different points in the object doesn't change. Okay, that's what we mean by rigid body transformation. So ideally we assume that. And then when we come to the image coordinate system, you have actually one coordinate system for the, say this can be your X, like the image coordinate, left image coordinates, okay, XY. And then this can be for the right image coordinates, again XY. Fine. And hence what will happen? These small xy are related to capital X, C, Y, C, Z, C. Okay, through a camera matrix. Okay, so there will be camera matrix which will be involving both the camera focal length information and then the rotation, translation aspects of the image plane to the camera coordinate plane and so on. Taking all these into account, this is a 2D 2x3 matrix. Okay, and then essentially here we are assuming, since we are assuming, usually what they do is X, Y, and 1 they will put, and then this will be 3x3 itself. Okay, and then this will relate the XC, YC, and ZC camera coordinates to the image pixel coordinates. Please note that here the information, in real coordinates, all the distances are in mm or centimeters. Okay, whereas in pixel coordinates, the information is in pixels. So there is a conversion factor that is usually required. Okay, based on the camera sensors. Okay, how much each pixel represents in real coordinates. Okay, in real, how much a pixel sees in real coordinate system. Okay, in real scene. So there is a conversion. These are all in pixel coordinates and these are all in real coordinates. There will be a conversion factor based on the sensor. 1 pixel equal to how many mm? Okay, in X direction, in Y direction, and so on. So this whole information is assumed to be known. Okay, and some things are given based on the camera and so on. Remaining things, some of the things we can design, say with respect to what are we measuring, the object dimensions. That is the real coordinate system. With where did we place our cameras? How did we place our cameras? That guides the camera coordinate system. Okay, and then the corresponding images where they get formed, we know because of focal length. And then we can calculate essentially what is the relation between them given the focal length and then pixel to camera coordinate conversion, which comes from the calibration. That means if we take a couple of pics, we can know actually what is the physical distance if we measure. What physical distance corresponds to how many pixels here. Okay, this process of establishing all this relation between the pixel coordinates to the camera coordinates to the real coordinates is referred to as calibration. Okay, this essentially helps us to give a relation in terms of these coordinate systems. Now the question is, if we observe an image of a scene, okay, in the left image, left camera and the right camera, okay, like left eye and right eye, how do we infer the depth information of the scene object or scene point? That is the next question. Hope these details are clear. Okay, again, come back to the same. Okay, I'm just assuming that there is a left camera here. Okay, and then there is a right camera here. Okay, and we are seeing a scene point here. Okay, and this scene point, when it is seen through the right camera, it is forming its image here. When we see the same scene point to the left camera, we are forming an image here. Okay, that's what we assume. And both gets formed at the focal length as I mentioned. Okay, so we will see now mathematically. And as we mentioned, so both are on the same horizontal line. We assume that both left and right cameras are on the same horizontal line for the simplicity. Okay, later we will see if they are not on the same horizontal line, what will happen in those aspects. Okay, so assume that this is the left camera and then this is the right camera. And since for ease of understanding here, as you can see here, when they are at the horizontal line, XL, YL can be anything, XR, YR can be anything. But if they are on same horizontal line, right and left cameras, what will happen is the same scene point will form its image on the right camera at the same row here. Here also at the same same column here. Here also at the same column. That means if they are horizontally aligned, then there will not be any shift. There is no shift in Y direction on the projections of the same scene point. Okay, if they are aligned like this, then there will be a Y shift as well. Okay, but if they are horizontally aligned, so what essentially I am trying to say here is YL equal to YR for a scene point, scene point when the cameras are horizontally aligned. Which cameras? Left and right cameras. Okay, so in that case, there will say if you would like to find out the information of a same scene point, where is it in this image versus in this image? Okay, if that information helps me to get the 3D perception, okay, in fact, it helps. So that we will see subsequently now. So if it helps to get the 3D perception, I need to find out where this scene point is in this image and the same scene point is in this image. That is referred to as finding corresponding points. Okay, when I want to perform that, if the images are horizontally aligned, then it is enough to search along the same horizontal line. That means, say if I know that the corresponding column equal to 10 in left image has the projection of this, then I need to search in the right image column equal to 10, that's all. But the row index may differ, because based on the distance, how far the object is, the row index will differ. Okay, so now let us mathematically try to put these details, okay, and see how we can capture the depth information, okay, when we have the projections. So first let us consider the similar triangles, say which is denoted by R, C, X, okay, and then O, for example, or some P. Okay, and then this is so this similar triangle, this triangle and this triangle are similar because they have the same angles here. Okay, so we can write D by alpha is equal to F by XL. Okay, I just use the this side by this side is equal to this side by this side, considering the similar triangles having same angle. Similarly, now I consider these two as the similar triangles, this by this and this and this. Okay, so then what we can write? D by B plus alpha is equal to what is that we can write? XXL. Here it is XR. Hope you are able to get now. So you can see the notations of XL and XR. In this, they are clearly denoted. So this is the left image and right image. Okay, and then we have actually a scene point here. It forms here, and then this is the XL. Okay, deviation from this point to this center to this. Okay, and then this is this is XR. Projection in the right camera. Okay, and then this is X. Similarly, this is XL. Okay, and both gets formed at focal length distance. And now I am considering this and this being the similar triangles. Okay, and then now using them, D by alpha is equal to F by XR. Okay, which I have written here. Using similar triangles around R. Okay, similarly, using the similar triangles here, this and this triangle, okay, and then this triangle are similar triangles here, having the same angle, okay, and then F by XL is equal to D by B plus alpha. Hope these are clear now. Using this, we can solve for distance D. dxr is equal to f alpha here, and this is dxl is equal to fb plus f alpha, which is unknown here. B is baseline, which we know, or which we can calculate from the how we place the cameras. XL, XR are being noted in the images. Distance is unknown. Alpha is also unknown. So what we can do, we can, in place of this, we can substitute this. And that gives us what? DXL is equal to FB plus DXR, or D into XL minus XR is equal to FB. That implies D is equal to FB by XL minus XR. FB by delta X, where delta X is referred to as the relative difference between the projections, referred to as disparity. So this is how we can calculate the depth information here. Depth is equal to FB by disparity, and hence this implies that depth is inversely proportional to disparity. That means if the scene point is closer, okay, wherever it is closer, then it will have a bigger difference in terms of the projections, relative projections with projection between X and Y cameras. Okay, we'll have the projections of X and Y in the X and Y cameras will be much higher. If the object is far off or the scene point is far off, then you can see that the relative difference between the projected points will be smaller. Okay, that's what is essentially being shown here. You can sketch the same with respect to the left and right cameras. Okay, for different scene points to observe the same. And this helps us to get the depth information or 3D information of the object. Is this clear? Are any questions now on this?
No, sir.
Yeah. This is usually referred to as disparity analysis in images or disparity to depth. So if I want to find the depth now, what essentially I need to do between the images? So if we wish to find the depth information, what should we do? Say we have a scene with which we have actually left image and then the right image. Okay, of the scene that are captured, and there are several objects in the scene. Okay, in both left and right images. Now what I wish to do is, given this information, okay, we would like to see what are the distance of different objects in this scene. What we know is depth information, depth is equal to, in terms of focal length and the baseline of the cameras, how is it related, is equal to FB by disparity. So given these images, what should we do to get the depth information? What we need to see, for each scene point here, what is the disparity? That's what we want to find. So if we write this as, say for each scene point, what we need to do is, in each point, what is the corresponding point here is what we need to see. For each XL, what is the XR? Okay, so because based on the depth information, XL difference between XL and XR differ. Okay, and hence there will be some disparity, and that disparity will help us to find out the depth information. So what we need to establish now, for each scene point, okay, what essentially need to find is, for each scene point, what is the corresponding point? So how do we find this? So suppose if we wish to find this now, for each of the points, how do we approach? Any idea on that? Say assume that for each point I want to find out what is the corresponding point that best matches this information around this point. What should we do?
We can do template matching.
Essentially, we can do template matching. This can again be done in two ways. First, find out the key points. Okay, around each key point, try to find out even key points here, which is the best matching key point. And then you can find out the correspondence at key points. Then what will happen? This is easy to do because key points are distinguishable from the neighborhood and so on. This gives us the sparse depth. That means only at key points we get the depth. The other way is consider all points, find correspondence. This gives us dense depth. Okay, so we will see in the next class some of the mathematical details for performing this task of correspondence. Essentially template matching only. So we'll just write a couple of equations for computing the correspondence in this setting. And then we will see how does it help to extract the 3D information. We will see with some of the visual results during that time. So if you have any quick questions, you can ask. Otherwise, we can conclude the class here. Okay, thank you then.